Now, Latin squares are matrices by definition, but we haven't been making linear algebra with them. We have just been treating them as arrangements of numbers because that's what they are. Let's do some actual linear algebra. Magic matrices and the Birkhoff-von Neumann theorem. Von Neumann theorem. I keep making this mistake. So let us now apply Hall's marriage theorem to linear algebra. Recall that n is the set 0, 1, 2, ... of non-negative integers. And we also set r plus to be the set of all non-negative reals. Unlike non-negative integers, I cannot really list them. Okay, and what is a magic matrix now? Well, there are two kinds. An n magic matrix means an n by n matrix M that satisfies the following conditions. First, all entries of M are non-negative integers. This is why this n. Second, the sum of the entries in each row of M is equal. Equal what? I'm not saying. I'm just saying all of those sums should be the same. And finally, the sum of the entries in each column of M is also equal. Actually, it turns out that if you require those two conditions, then the sum in each row will be the sum in each column. You can probably figure this out before I even state this, but I will state this in 5 minutes. Here are two more definitions. First, is a variant of this of the n magic matrix where you replace non-negative integers by non-negative reals. So n gets replaced by r plus. And finally, what is called doubly stochastic matrix. This is an n by n matrix whose entries are non-negative reals. And again, the sums should be equal in each row and each column, but now they actually require that they're equal 1. Let me just say is 1. So these are two variations of the same idea, and they're closely connected. We can often prove a thing about one of them, and then it will follow for the others, or something very similar will follow for the others. So let me give a bunch of examples, which I think will clarify the connections. So first of all, again, the stupidest possible example. How do you get an n magic matrix? Well, you put the same value everywhere. For example, let's put a 1 everywhere. So let's look at the n by n matrix. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. 1, 1, 1, 1, 1, 1, 1. This is clearly, well, this is n magic and also r plus magic. I mean, any n magic matrix, of course, is r plus magic. Okay, this matrix is not doubly stochastic, well, unless n equals 1, because the sum of the entries in each row or in a row or column is n, not 1. But of course, we can easily fix it. We can just divide this matrix by n. Thus, if we divide this matrix by n, it becomes doubly stochastic. This is the simplest possible example. Here is a less simple example. Here is an n magic 3 by 3 matrix. You can check that sum every row. This gives 12, this gives 12, this gives 12. Alternatively, sum every column. This is 12, this is 12, this is 12. All the sums are equal, so the matrix is magic. At this point, if you know magic squares, you see the connection. But magic squares have to satisfy, again, they have to satisfy a few more properties. The numbers usually have to be distinct, which is not true for those matrices. But we don't care. For us, it's the sums and and also in the magic square, I think the sum and the diagonal should be the same. This is not true in this matrix, but we don't care. We care about the rows and the columns. Okay, so once again, dividing this matrix by 12 gives a doubly stochastic matrix. And finally, here is an important example. Any permutation matrix is it's all of the three. It's N magic, R plus magic, and doubly stochastic. So what is a permutation matrix? A permutation matrix is an N by N matrix whose entries are zeros and ones, and which has exactly 1, 1 in each row and exactly 1, 1 in each column. For example, here is a permutation matrix. I'm going to fill it with zeros, and then I'm going to put ones, for example, here. Each row has only 1, 1, and each column has only 1, 1. And they're called permutation matrices because they correspond to permutations. If you look at the columns, in the i's column, if you say the 1 is in the i's column is in the position sigma I, then sigma is a permutation of the numbers 1 up to n. Okay, so note that for any n and n, there are n factorial many permutation matrices of size n, and they are in bijection with the permutations of 1 up to n. So, but this is, so permutation matrices are a pretty simple example of this kind of magic matrices. However, it turns out that these permutation matrices are, in a sense, the building blocks of all magic and doubly stochastic and particular matrices. Namely, the following holds. This is the so-called Birkhoff-von Neumann theorem. That's John von Neumann. I'm not sure which of the Birkhoffs this is. So again, let n be a non-negative integer, and I will state it for all three kinds of matrices. First of all, any n magic n by n matrix is a finite sum or can be expressed as a finite sum of permutation matrices. And once again, the converse is obvious because every permutation matrix is magic, and if you sum a bunch of magic matrices, you get a magic matrix again because all the row sums get added, all the column sums get added. Next, the analogous claim for real numbers, so any R plus magic n by n matrix can be expressed as, and now I cannot take finite sums because finite sums would only give me integers. So I have to use R plus linear combination of permutation matrices. So in other words, it can be expressed in the form lambda 1 p1 plus lambda 2 p2 plus dot 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 plus lambda k pk, where lambda 1 and so on are non-negative reals, and where the p's are permutation matrices. And finally, any doubly stochastic n by n matrix can be expressed. So the right way to say it, of course, is as an R plus linear combination of permutation matrices such that the coefficients, so the lambdas, add up to 1. But this has a name. It is called a convex combination, because in convex geometry, a convex combination is a point in the convex hull. So if you view all of those matrices as points in an n-squared dimensional vector space, then a convex combination of permutation matrices, it's basically a matrix lying somewhere in between those permutation matrices. It's part of the convex hull. But you can ignore all of this and just view it combinatorially. So I should say matrices. And now I should say satisfy lambda 1 plus dot 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 plus lambda n equals 1. So I will sketch a proof of this fact using either Frobenius or Hall. I think Hall is the most convenient one. So Hall's marriage theorem. First, two simple lemmas. So that will be used in the proof. I don't want to call it. So the first one, I don't call it. I'm not calling it a lemma because it's kind of interesting in its own way, but it's pretty obvious. Let A be an n magic or R plus magic matrix. Then the sum of all entries in a row of A equals the sum of all entries in a column of A. So basically, these two numbers, they're not just equal among themselves, they're also equal to each other. And the proof is easy because both sums equal 1 over n times the sum of all entries of A. And next comes another lemma. This lemma is going to be crucial. And now I'm going to call it M. Sorry for this, because A will soon mean something else. Okay, so let M be an n magic or R plus magic matrix. That is not the zero matrix, because of course the zero matrix is magic, but that's boring. And by the way, the finite sum can be empty, so the zero matrix is expressible as an empty sum of permutation matrices. I'm not going to make an exception for this. It fits the rule. You just have to accept empty sums. Okay, so let M be an n magic matrix. It's not the zero matrix or an R plus. Then there exists a permutation sigma of the set 1 up to n, such that all entries M1 sigma 1, M2 sigma 2, ... Mn sigma n are non-zero. And of course, non-zero means positive because they're non-negative. So for example, if n equals 3 and m equals 2, 7, 1, 0, 1, 9, 8, 2, 0. So for example, you couldn't take this permutation because this 2, 1, 0, the 0 is not non-zero. But you can take this permutation, 8, 1, 1. So the permutation here sends 1 to 3 to 3 to 1. So the permutation sigma that sends 1 to 3 to 3 to 1 has this property. Proof of the lemma. How do we find a permutation? Well, we already have seen some permutations that we found using Hall's marriage theorem. This is no exception. First of all, let S denote the sum of all of the entries in any given row of M. As we already know from the previous proposition, the sum is the same in each row. And okay, sorry, no. Let S denotes the sum of the entries in any given row. It doesn't matter which row we take, since our matrix is magic. Then S is also the sum of the entries in any given column of M by the previous proposition. Note that S is positive since M is not the zero matrix, but well, has non-negative entries and is not the zero matrix. It has non-negative entries, but at least one of them is actually positive because it's not the zero matrix. So the sum is positive. Okay, now let x be the first n positive integers and y be the first n negative integers. Let G be the simple graph with vertex set x union y. This is something that we've been doing several times now. And this edges defined as follows. A vertex I in X shall be adjacent to a vertex minus J in Y if and only if the entry Mij is positive. So here Mij denotes the ij's entry of the matrix M. So row I, column j. Okay, there shall be no further adjacencies. So as usual, Gxy is a bipartite graph. And now, for example, for this matrix that we have here, I can draw it. So here are the, I should probably leave some space open. Yeah. Let me draw it now. So here are the positive vertices. Here are the negative vertices, left or right, but we just decided to make some of them positives and the other negatives. And now, oh, actually, I can draw a straight line. Why am I doing all this freehand thing? So the first row has non-zero entries everywhere. So the first vertex 1 is connected to all of them, all of the right vertices. The second vertex, the second row has positive entries in columns 2 and 3. So 2 is connected to -2 and -3. And 3 is connected to -1 and -2 because of where the third row has its non-zero entries. So that's a big bipartite graph. And for you see immediately that it has a perfect matching. For example, what is a good perfect matching? This, and this edge form a perfect matching. And this means that if you take the third entry of the first row, the second of the second, and the first of the third, they're all non-zero. And that's the permutation you're looking for. So let's explain why this always exists. We shall now prove that it satisfies the whole condition. That is, we shall prove that every subset A of 1 up to n satisfies the number of neighbors as at least the number of elements. To that, well, assume the contrary. Thus, there exists a subset A that does not satisfy this inequality. Consider this A. And without loss of generality, we assume that A equals 1, 2, ... k for some k. Otherwise, we permute the rows of our matrix. Permuting the rows doesn't change all of the sums, so it's still gonna be a magic matrix. So all positive entries in the first k rows of A are concentrated in fewer than k columns. Because this is saying, well, the columns in which these positive entries are the neighbors of the set A. And we've assumed that there's fewer neighbors than elements of A, so fewer than k. So in the columns in which they lie are the columns in n of A, but the size of n of A is less than the size of A, which is k. Therefore, the sum of these entries is smaller than ks, because in each column the sum is s, and if you live in fewer than k columns, the sum is, well, actually at most k minus 1s, but all we need is it smaller than ks. On the other hand, however, the sum of these entries equals ks, because they're also positive entries in the first k rows of A. And in each row, the sum is s. So if you sum the positive entries in k rows, you should get ks. And summing zeros doesn't change anything. So it doesn't matter if you sum all the entries or the positive entries. So we get a contradiction, because a sum cannot be smaller than ks and equal to ks at the same time. And this contradiction shows that our assumption was false. Hence, the whole condition is satisfied So the Hall's marriage theorem yields that G has a perfect matching. And now we play the usual game. So let this matching be 1 up 1 comma minus a1, 2 minus a2 dot dot dot, n minus an be this perfect matching. Then the numbers, the a's are distinct because it's a matching. So we can find the permutation sigma of 1 up to n such that the a's are the sigma i's. And this permutation sigma then satisfies mi sigma I greater 0 for all I, which is what we wanted. All right, so the lemma is proved. But how do we prove the theorem? Well, essentially it's applying the lemma many times, but I will not go into the details here. I will put some details into the notes. Here I will just give a proof by example. And I will be talking about part A in particular, because the other parts are kind of similar. So here is what we're proving. So let's start with part A. So let M be an n magic n by n matrix. How can we express M as a sum of permutation matrices? And again, I'm going to use this example. For example, let n equals 3 and M be this matrix. So how do you write it as a sum of permutation matrices? You try to start with the first element. Find a permutation matrix that you can subtract from M in such a way that the result will still be n magic. Well, first of all, the result will clearly satisfy these conditions that the sums will be equal. The only problems that you could get is that some of its entries could no longer be positive or non-negative. So, for example, if you subtract the wrong permutation matrix, if you, for example, subtract this permutation matrix, and I will actually leave out the zeros. Every missing entry is a 0. If you do this, you get this, which is not a magic matrix simply because there is a negative number in it. That's not allowed. So I have to find a permutation matrix that I can subtract without creating negative numbers. And fortunately, from the lemma, I know that there is one, because there is a permutation such that all the respective entries are non-zero. For example, let's try this permutation. So let's subtract this matrix. This gives you 7, 0, 0. Cool. We're getting closer. Eventually, our goal is by subtracting enough of those matrices to get the 0 matrix. And while we don't have the 0 matrix yet, but we have increased the number of zeros in our matrix, which means we're kind of getting closer. So what are we doing? Try to subtract a permutation matrix from M in such a way that the result will still be an n magic matrix. Here's one way to do it. Okay, now let's do this again. What permutation matrix can you subtract from this one? Well, you can subtract something like this. So basically you could subtract this. Okay, but even better, instead of subtracting it only once, let's fast forward it. Let's subtract it 7 times, because all of those entries are at least 7. So even if you subtract it 7 times, they will still not be negative. So, okay, now we have to subtract the 7 from each of them, and you're getting this. So we have subtracted a permutation matrix 7 times, because all the relevant entries are greater or equal 7. Okay, and now we're even closer. Basically, this is a permutation matrix times 2, but let's forget about it. Let's just do this again. What permutation matrix can we subtract? Well, we can only subtract this one. And because there is 2's in everywhere, we can subtract it twice. And now what we get is really the zero matrix. So 0, 3 by 3. So now if you back substitute, you see that the original matrix M, it is what we subtracted first, plus what we subtracted second, plus what we subtracted third. So this is clearly a sum of how many? 1 plus 7 plus 2 permutation matrices. And this argument goes through in general because the lemma tells you that there is always a permutation matrix that can be subtracted. Moreover, if you if you subtract the respective permutation matrix, so if you subtract the maximum possible multiple of the respective permutation matrix, then at least one non-zero entry of your matrix becomes 0. So it is clear that sufficiently many, actually at most n square, such subtractions will lead you to the 0 matrix. Thus, part A can be proved, and part B is analogous. Now, for part C, just notice that. So, what is part C saying? Of course, doubly stochastic matrices are R plus magic, so you can apply part B and observe that the coefficients, the lambdas, have to add up to 1 in order for the matrix to satisfy the doubly stochastic requirement. Because basically, if you take this expression, if you look at this matrix, the sum of the entries in each row will be lambda 1 plus lambda 2 plus 2 plus lambda k. So if you get a doubly stochastic matrix, then the sum has to be 1. So we're not actually getting anything new, except I'm seeing there is a typo here. The n should be k, and here too. So much for the Birkhoff-von Neumann theorem. So usually people do this as a so the proper theory of which this result is part of is called linear optimization, or the theory of polytopes. But it's also relevant for the theory of inequalities, in particular for majorization theory. This doubly stochastic matrices are, in a way, matrices that transform tuples of numbers into other tuples of numbers that are in a way closer together. So, for example, in Mass 504, you see a bunch of applications of doubly stochastic matrices and even of this theorem. So it's not just combinatorics where perfect matchings can come very handy.